another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. I want to start off this episode by revisiting part of the topic we covered last week, where I mentioned how I created a CI/CD pipeline, or a continuous integration, continuous development pipeline. So in that segment, I mentioned using my credentials to log into the Docker server to deploy the code. And I don't think I did the best of job explaining how that works, and I don't want to give you the impression that I hard-coded the credentials into the GitLab ci.yaml file, because that's not what I did. So GitLab allows you to securely store environment variables that you want to use in your YAML file, like within GitLab itself. And you can also configure it so with the specific purpose that once the pipeline runs and the output gets logged to the log file, the variables that you specify that you want to be secure, like an SSH key or a host name or something like that, won't actually be displayed in the log file, and it'll only display the variable name. So that's how I set up the credentials for the Docker server, so I'm not actually hard coding them. And for that, I use the IP address of the server, the SSH key, and I would have done the user too, although the username wasn't long enough, since I think it had to be like at least 8 characters or something like that in order for this kind of masking thing to work. Otherwise, it just kind of outputs. But I mean, as the IP address and the SSH key, which are probably the most important things, are, secured that way, so it's not a big deal. So I just wanted to kind of revisit that, just in case some of you were thinking I was being an idiot for hard coding the credentials inside the YAML file, because that obviously would not be a smart move. But that's not what happened, so I just wanted to clear that up. So let's start off this episode with the trivia question for the week. And this week's trivia question is going to be a little bit different than some of the past ones we had, because I'm going to give you 3 options, except 3 of the options are correct or truthful and 1 is not, and you'll have to tell me which one is false. So with that, let's get into the trivia question, which is, which of the following is not true about the original iPhone? Is it A, you couldn't rearrange apps on the lock or on the home screen? B, the camera was capable of capturing video at 720p 30 FPS. C, there was no App Store originally. Or D, the CPU was developed by Samsung. So which one of those 4 is not true? And that is your trivia question for the week. So I saw quite the hilarious article by The Verge, and there's also I think a video for it as well. Our boy, the Zuck, our day to be upon him, has tried out the Vision Pro, and he has some thoughts. So according to him, he says, quote, I don't just think that the Quest is the better value. I think the Quest is the better product, period. Now, I can't speak to whether the Quest 3 is better than the Vision Pro, or even a better value than the Vision Pro, because quite honestly, I've tried neither. So I don't exactly have an informed opinion on which one is actually better, But from the kind of analysis I've heard online from people, the Quest 3 is definitely a pretty good value for the price, but the general consensus, at least that I've heard, is that the Vision Pro is better overall than the Quest 3, but that's not necessarily to say that it's however many times the better value. So for instance, I think Zuck mentions that the Quest 3, I think, is 7 times cheaper than the Vision Pro. So for instance, I don't think the Vision Pro is 7 times better than the Quest 3, but based on what I think people have been saying, it still kind of is better than the Quest 3, although maybe not, like I said, 7 times better. But the reason why I bring this up, and I think it's funny, is because, let's be real here, folks. What did you expect him to say? Did you expect him to come out and say, wow, Apple really knocked it out of the park on this one and made one heck of a headset? Of course not. Of course he's going to say that his product is better. That's like if Sundar Pichai, who's the CEO of Google, came out and said, I tried AWS, or Amazon Web Services, and it is so much better than the Google Cloud Platform. Which, of course, he's not going to say that because the Google Cloud Platform is his competitor to AWS. So, of course, he's not going to say his competitor is better, even if some would argue it is better by a long shot. Now, I've used both AWS and Google Cloud Platform, both only the free tier. Although I will say, one thing that is very annoying about AWS is trying to figure out their pricing structure is like trying to read a foreign language and do your taxes in a foreign language. You can do it, but it's not exactly the most straightforward thing. At least that's been my personal experience with AWS. And the one time that I did let my free tier expire, they were charging me way more than I thought should have been charged, and then promptly canceled my account with them and moved to a different provider. But that is, I guess, one thing with Google Cloud's platform is I think their pricing is a little bit more straightforward. Now, as far as value to value, I haven't really used much of either of them, so I can't necessarily speak to that. But the point of this being, the CEO of a company is not going to say another company who is a competitor to them makes a better product than they do. Like, could you imagine Elon Musk saying that Ford makes better EVs than Tesla does? Of course he's not going to say that. Now, you can argue whether Ford does make better EVs than Tesla, but the fact of the matter is, the CEO of a company is not going to say that their competitor makes a better product than they do. So I just found it kind of funny and a little odd that the Zuck felt the need to give his personal review of the Vision Pro and just to say how much better the Quest 3 is. I don't know if this was like him scared of and trying to, be like, like that meme with the dog when the house is on fire and he's like, this is fine. I don't know if that's what the Zuck's mindset was, but I just kind of thought it was rather kind of funny that he felt the need to say that when we kind of all knew, like, what else was he gonna say. But with that, let's get into this week's cybersecurity tip. So this week's cybersecurity tip is kind of more of an awareness thing and how you can protect yourself against social engineering attacks, specifically social engineering attacks to bypass multi-factor authentication. So one of the ways that multi-factor authentication can be bypassed is by adversary in the middle attacks, So basically deceiving users to make them think that they're logging into a legit site, and then they harvest your two-factor, and then they use that two-factor that you just entered to log into the real site and basically bypass your two-factor authentication that way. Another one is MFA prompt bombing, which I find is kind of a funny name, but basically taking advantage of the push notification feature on certain modern, authenticator apps. So depending on how the authenticator is set up with the website, some websites will allow you to basically send you a push notification, and you can just like tap on it and say like approve or deny, rather than having to like open the authenticator app, view the 6-digit PIN code or whatever, and then enter that. So basically the idea here of the prompt bombing, I guess, is they just keep spamming you the prompts, and then eventually you'll just hit approve or something and then let them in. Probably shouldn't do that. The next one is service desk attacks, which I've actually heard about this happening before, where someone from like the help desk or something will basically try to call you and say something about like an issue with your account or something, and to verify like your two-factor code or something like that, to basically impersonate them trying to help you out, but really they're just harvesting your information. Pretty classic social engineering attack, but I mean that's like you've all heard of the that prince, the Saudi Arabian prince, I think, that's always sending emails saying that he wants you to inherit his fortune or whatever, or pretty much any kind of help desk type thing. Or another classic one is bank accounts saying, I say bank accounts, of course, they're not actually the bank accounts, they're no good evil people, but send you phishing emails basically saying, oh, we detected suspicious activity on your account, log in to verify that you made this transaction or whatever. And then of course the actual link they give you is a malicious link that isn't actually to your bank account or whatever, and then when you go to log in, they just harvest your information and then go log into your actual bank account, and then they can basically do whatever they want. So this is basically the same thing, just with your multi-factor authentication. And then this next one is kind of one of the reasons why, if you can help it, you shouldn't use SMS for your two-factor. And that is SIM swapping. So essentially, part of the reason with SMS, we talked about this in previous episodes, is one, SMS is not encrypted, so your two-factor code is going over the air unencrypted. So in theory, someone could be sniffing the packets, sniffing the message, and get your two-factor code that way. But also because it's tied to your phone, if there's what could be a chance that an attacker could do some exploit to essentially clone your SIM card, or somehow get access to your phone number to divert the text messages or get a copy of the text messages to them, in essence bypassing your two-factor check because they now have access to it. So yeah, this is kind of, we're kind of blowing holes in multi-factor authentication here with some social engineering attacks, but that's the thing with cybersecurity, though. There is no foolproof solution, and that's why it's called multi-factor authentication, because in theory, you should also be using this in tandem with another form of authentication, like a strong password or biometrics or something like that. So even if one of those lines in the chain gets compromised, you don't then get compromised as a result, right? It's the Swiss cheese methodology, right? Every type of cybersecurity principle has holes in it. It's just a matter of how big they are or how small they are. But regardless, there are holes in them. But if you stack enough of these layers on top of each other, you're not secure because, like I've said before, the only way you can be secure is essentially if you never log into the internet, never have any kind of account, anything, not a zilch, nothing. You basically have never existed in the digital world. You have no bank account. All your money's stuffed up. Well, even if your money's stuffed under the mattress, you could still get robbed. But point being, you can't have your account stolen if you don't have any accounts in the first place. Your computer can't get hacked if you never have a computer, or if your computer is always off, unplugged, and in the corner. It can't be hacked remotely. So yeah, there is no silver bullet when it comes to cybersecurity, but the point of this is that you should have multiple layers of cybersecurity in order to better protect yourself. So in the event that one of your lines of defense fail, you have other lines that can hopefully help defend you against attacks, cyber criminals, and all that jazz. So that is your cybersecurity tip for the week. Now, the main topic that I wanted to talk about for this episode is probably one that C++ evangelists are probably going to hate me for, but I'm going to do it anyway. But before that, let's get into what nerdy stuff have I been up to this week. So this week was pretty much continuing my refactor process for my video game that I'm working on, which I will say, one way that you know you had a good, successful refactor session is when you change tons of lines of code and your program doesn't perform any differently, doesn't change at all, it functions just like it did before. That's when you know you had a good refactor session. I guess the only caveat I'll add to that is if you're trying to refactor for some kind of speed optimization or performance, then assume you would, in theory, wish to see the exact same thing as before, just maybe a little bit faster. But this is one of the reasons why you should ensure you have good test cases to test your code, to make sure when you go through these massive refactor processes and changing a bunch of stuff, you can adequately test and verify that your code indeed is functioning as it did before. Because one of the most common ways that bugs end up in software in general is because edge cases weren't checked. So it's really easy to do a refactor, test the, basic functionality, realize it works, and be like, all right, I'm good, only to then come back days, weeks, months, potentially years later and realize, oh, wait, this one edge case causes the program to crash. That wasn't how it was supposed to be. And then you realize your refactor, you forgot to account for some edge case. So that's one of the reasons why you'd want to make sure that you have adequate and thorough test cases to thoroughly test your code. So when you go through one of these big refactor sessions, you can really easily and quickly verify that, yep, indeed, your code is working functionally just like it did before and there aren't any issues. So that was part of the work I did. And then the other part of the work I started on was creating a dialogue manager, basically to handle like multiple lines of text and potentially and prompt users for input. Now, I already had a function, if you will, that will essentially display multiple lines of text, but it only displays 2 lines at a time. So basically what the dialogue manager class will do is it'll manage, multiple sequences of that, plus also some basic user interaction of, yes, no, or some easy basic prompts like that. The funny thing is, I implemented that, and then I think I'm trying to remember when I implemented it. I think I implemented that over the weekend, and then I kid you not, as soon as I got it implemented, I completely refactored it and redid it into a better solution, which we'll get into in a little bit. But before I got to redoing it, of course, I had to test it. So this is where things got interesting. But I guess one thing that I should point out first is if you've been listening to the episode for the podcast for the past few weeks, you'll know I've been really diving into the battle scene, and I was going to work on like learning new moves, and now why the heck am I doing dialogue? That seems kind of off topic, but if you've ever played Pokemon before, you'll know kind of there's a lot of dialogue that goes on when asking if you want to learn a new move. So I figured I'm going to have to do dialogue eventually. I might as well just do it now because this is a pretty good use case for it. So anyway, that's why I got sidetracked on this tangent of dialogue. But anyway, as soon as I implemented it, the first iteration, I decided I should definitely test this just to make sure that it's still working on other operating systems and I don't have memory leaks and all that good stuff. And I tried it on Linux, and oh boy, let's just say things did not go according to plan. But I want to start by saying I have no idea what kind of witchcraft macOS's C and C++ compiler is using, but it managed to take my dialogue system, which after running it on Linux, I realized was memory error-ridden and memory leak prone out the wazoo, and it still somehow managed to run this perfectly without issues. And how do I know this? Well, of course, one thing I've mentioned is I do not all, but a good amount of my development on Mac OS. And of course, I got it working because that was the reason why I was testing it on Linux or wanting to test it on Linux. And it worked fine on Mac OS without any issues whatsoever. And then I tried to run it on Linux, and needless to say, it crashed and burned hard. And when I say hard, I mean real hard. Like, the program just abruptly stopped when it got to the dialogue portion. And not only that, but then I decided to run it through Valgrind, which, if you're not familiar with Valgrind, it's a memory leak checking tool. And so one thing with Valgrind is it'll print out error messages if it detects memory leaks. And I ran the program through Valgrind on Linux, and I kid you not, the error list was so massive I could not scroll to the top of it because it had fully maxed out the terminal. And I tried, scrolling as much as I could, and it just would not do it. There was just way too many errors. And from the looks of it, it almost seemed like the program was trying to, allocate all of the system's memory before the operating system was like, nope, you're trying to allocate all the memory, you're dead, and just totally killing it. So yeah, I have no idea. Well, actually, now I do know why it was doing that, but I have no idea how it managed to crash and burn that hard on Linux, yet work perfectly fine without any noticeable issues on Mac OS. So I don't know, like I said, I don't know what witchcraft Mac OS is doing with its compiler. But this is why you test things, because when you're dealing with a compiled language, you're not guaranteed to get the same outcomes on every system you write the code for. Now, if you're doing something like with Java, for instance, that runs in its own Java virtual machine, this isn't an issue, but C and C++ are different because the code gets compiled down to machine code, and different operating systems have different ways that they handle various system calls, so that's why things can get messy. But in essence, the issue ended up being that I was using a single pointer to reference an array rather than a double pointer, and that ended up being the issue. But like I said, this isn't the first time that macOS has done weird witchcraft like this, and I cannot tell you how many times I've ran into issues where macOS compiles and runs just fine, and then I get compile errors on like Linux, for instance, because I'm missing an include file that for some reason macOS was happily able to, I guess, include for me or something. So my best guess is macOS is essentially looking at the code that you write, understanding what your intent is, and then essentially rewriting things that don't actually work so it'll work, and kind of doing like a little bit of rewriting for you. And if you're thinking this kind of sounds spooky and it shouldn't do that, I hate to break it to you, but all compilers do this regardless of platform, because if you've ever heard of compiler optimization, that's essentially what's going on behind the scenes. The compiler is interpreting what you're writing as far as what your code is trying to do, and then will find tricks and ways to rewrite the code in a way to more optimize it or improve the performance of it for the given platform you're building for. So it's not necessarily a new concept for a compiler to take your code and change it. One way that you can really see this in action, if you have especially if you have optimization turned on, is if you have a for loop that will essentially do absolutely nothing. The compiler will sense that you're writing a for loop that does literally nothing and will just completely skip it entirely. So there are things like that compilers can do in order to optimize code. So it's not out of the ordinary for a compiler to essentially rewrite your code for you. But the thing that's weird is that on macOS anyway, it seems it can take code that literally is not functional on other platforms and will somehow make it functional. So, like I said, I don't know what witchcraft it's doing behind the scenes, but apparently on the other hand, Linux is just like, you want to just go shoot yourself in the foot? I mean, hey man, it's your funeral, whatever, here you go. So it seems like Linux is definitely more literal, literal in the sense, and macOS is kind of more fluid, if you will, and it's like, okay, I see what you're trying to do. Obviously, I don't know if that's actually what's going on, but at least from my experience developing on both platforms and trying to write code for both platforms, I've had that experience multiple times where code works just fine on macOS, and then we'll have some serious issues on Linux because I guess macOS just happened to do stuff for me, which I want to kind of touch on that a little bit more, because on the one hand, it is very nice that macOS was able to take my non-functional code and make it work. But on the other hand, if I didn't test it on Linux, for instance, I would not have known that the code I wrote was actually non-functional. So in a way, I kind of got to give the points here to Linux for being the better development environment and platform, for the sake of it actually makes sure that you can write usable code. Because I think the only time I've really had issues with code I wrote on Linux not working for Mac OS is if there was a specific like Linux system call that I was invoking that wasn't on Mac OS, and Mac OS you'd have to do it slightly differently. Aside from that, I don't think I've ever ran into an issue where code that worked on Linux didn't work on Mac OS, but I've had many instances where code on Mac OS doesn't work on Linux, and it's not due to the fact that I'm using a system call or something that's specific to Mac OS. It's just Mac OS's compiler managed to hide the errors in my code from me, and in essence kind of made me write worse code because I wasn't catching that. But this is why we test things. This is why you have development environments. This is one of the reasons why I said all developers should have a home lab, so you can have multiple environments to test your code on, because it's better to catch it early than to make a ton of changes, implement a ton of features, only for everything to blow up in your face, and you spend days or weeks trying to debug and troubleshoot why your code is not working. And we both experienced this last year I think it was over the summer, something like that. It was a few months ago when I was doing a massive refactor process trying to wipe out all the memory leaks in my code, mainly because I hadn't taken the time beforehand to properly test my code for memory leaks. And then, of course, I ended up spending multiple weeks trying to get all those memory leaks out. So I've definitely learned my lesson. And after implementing a big feature like that with the dialogue system especially, I made sure to thoroughly test the code on Linux, and I'm glad I did, because that definitely could have bitten me. Now, getting into the fact that I mentioned I essentially implemented the dialogue and then immediately refactored it. So this was for a rather understandable reason, I think. So the original version took 3 different arrays as arguments. So you can already see why this would not be scalable at all. So it took in an array of strings, which would be the dialogue. It took in another array of strings, which would be the interactions that you would prompt the user for. And then it would take in an array of integers that would correspond to the interactions. So if, for instance, on the first interaction you selected the second option, the second option of the first array in that integer list would correspond to that. So for instance, if the second option was no, that option in the integer array would map to what no would be. It would map to the appropriate line in the dialogue to essentially allow you to jump around the dialogue. So this worked, but like I said, it was not scalable, and trying to actually implement it, I was having multiple counters to keep track of everything, and I wasn't even sure if my logic was right. It was really hacked together. I was definitely dreading having to implement this in the future, because making 3 different arrays was just not going to work. So I decided to refactor it, and I'm not sure this is going to be the final solution, but I'm a lot happier with it now. So now it only takes a single array of strings, and in that array of strings, you basically can encode all the data that you previously had to do in 3. So now what I have programmed is I have special delineators to essentially signify this line is not actually dialogue, this is an interaction. This is the end of dialogue. So before, what I was trying to do was count how many lines of dialogue you've read, and if you got to a certain point, then you would be done. So definitely really messy, not scalable at all. So this new version, basically whenever you get to one of those lines that has the delineator, this is the end of the dialogue, it just is done. So that definitely was an improvement, knocked out a counter. And then the interactions portion, I basically encoded that so you have like I said, a delineator to say this is an interaction, and then you have each one of your interactions that you want as options separated by new lines. And then after the interaction, so for instance, if you want the interaction to be yes, after yes, you have another delineator that basically points to where in the dialogue you want to jump to. So for instance, you can put the actual line number itself, or you can just do a plus or minus. So for instance, if the answer is yes, then you go to the next line, you can just do a +1 rather than having to actually figure out what line it is. Or if you don't put anything, that'll just wrap you back around to the first option of the dialogue. So I'm definitely really happy with the quality of life improvement that it gave me. Now, like I said, I'm not sure if this is actually going to be the final solution. I have thought about doing like a tree structure, like actually creating a tree structure as a data structure and then basically populating it that way. But one thing I wasn't quite sure about was how I'd handle interactions. I guess I could probably do a similar thing as how I have it implemented now. But that would definitely take a serious amount of re-architecting. And at least at the moment, I'm pretty happy with how it is now because it's a lot easier to just write lines of dialogue and then add some delineators for the interactions, especially compared to writing 3 separate arrays. So it's definitely more scalable, be a lot easier to implement. So I think I'm at least going to try it for right now, and we'll see where this goes. But yeah, definitely a big overhaul. Kind of funny, I think, that I implemented something and literally as soon as I realized it's working, I completely redid it. But that's just how it goes. And, handling the tech debt, because that would have been some massive technical debt trying to work with that original system. That's for sure. So that's what I got up to. But I think now we should probably get into the potential hot takes, if you will. And the reason why I kind of thought about this was because I had been debating on how one of the ways I was implementing the dialogue is using some of these things from the C++ standard template library, the containers. And then there's also other ones that I'm going to touch on too, the smart pointers. But first, let's start off with the containers. So in the C++ standard template library, it comes pre-packaged with various containers. So this is your vectors, your arrays, and I should mention there is a difference between the standard template library array container versus just your standard array. So your standard array is like, you call malloc on something for the size of, or you do your square brackets and put however big you want the array to be. That's one thing. And then you have a separate container for arrays, which you can do a lot of other things. You can most notably get a size of the array, which is very helpful. You can't do that with normal arrays. Then you also have like other data structures like sets, stacks, maps, that kind of a thing. And I'm not going to lie, they are very nice and super convenient. And I've actually used a few of them inside my game itself. I've used vectors a little bit. Pretty much my entire serialization and deserialization is based on vectors. My string parsing is mostly based on vectors. I use maps also for mapping like move sets and whatnot, so I can just plug in a level and see if there's a move associated with it. So they are definitely super nice, super convenient. But I will say there is a reason when you are first learning data structures that they have you implement your own, and don't let you use the ones from the standard template library. And the reason for this is you get a deeper understanding of how these data structures work and basically computer architecture as a whole. Because it's one thing to use the standard template library of a stack and create a stack to manage whatever you want to manage. It's an entirely different thing when you have to write the stack data structure yourself. Because you can implement a stack and, you get the whole, first in, first out thing, and you kind of get how it works. But actually having to write the code to implement that yourself, you gain a much deeper understanding of, how these data structures work. Now, I'm not saying that you should never use the standard template library containers, because I'm obviously using them and they are a serious quality of life improvement, not to mention the fact that these container structures are almost guaranteed to be better, let's be honest, be better than anything you're going to write, definitely better than anything I'd write. Because they're developed by super smart people, but also, the language itself, once you start turning on optimizations, it's basically, indistinguishable from, a standard C style kind of array type thing, as we'll kind of get into a little bit later. But that's not to say that these types of containers don't have their trade-offs, because as we mentioned in one of the earlier episodes of this podcast, we kind of did quite a bit of a deep dive into how like memory allocation works with C and C++. And in that episode, we kind of talked about one of the trade-offs using like fixed-sized arrays versus vectors. And one of those trade-offs is fixed-size arrays, they're always going to take up the same amount of memory, where vectors can scale dynamically, which you can scale an array, a standard array like in C or C++ dynamically using something like realloc, for instance. But one of the issues that you run into is when you resize an array like that, or resize a vector, the memory's got to go somewhere. So sometimes, like if you're using realloc, you'll sometimes just extend the memory block so you don't actually have to do any copying. But there are instances where the memory block that your pointer is currently pointing to isn't large enough to account for the new size you want. So you'll have to get a pointer at some other point in memory, which means in order to keep all your data, all that data has to be copied from the one memory location to the other one. And this accrues overhead. So especially when you're dealing with really large chunks of memory, which is one of the reasons why one of the optimizations built into these dynamically allocating data structures, and if you ever want to dynamically allocate your own, is essentially multiplying everything by 2. So in essence, when you start out, you don't increase the memory footprint that much, but as your data structure gets bigger and bigger, the cost of having to copy all that memory gets more and more expensive. So you want to minimize how many times you have to do that copy operation. So if you multiply everything by 2, once you get really, really big, it kind of ensures that you're not doing a whole lot of copying. And it's kind of a good balance between limiting how much copying you have to do, but also minimizing how much space you're taking up by allocating memory. But that is one of the trade-offs that you run into when dealing with like dynamically allocating data structures that do all that for you. But at the same time, if you were going to implement your own version of a dynamically allocating array, you would have to, come up with all that yourself. And the one nice thing about the standard template libraries, those containers, is basically, once you turn optimization on, there's essentially no difference in performance. Now, one thing I did notice is I did kind of a little experiment to test this, basically taking just doing a standard C style dynamic memory allocation, just creating an array, creating a pointer, mallocing some initial memory, and then running through a for loop, checking if the size is too big. If it is, multiplying it by 2, calling realloc, and that kind of a thing. And then another version using a vector and just doing pushback all the time. And what I found is if you don't have optimization on, it's noticeable if you run the time function and actually time the program execution. But if you're just doing the eye test, you can't really tell. But the vectors are slower if you don't have optimization turned on. If you do have optimization turned on, they're essentially identical, well within the margin of error, which kind of points and gives credence to the fact that these, standard template library containers are very well optimized. And if you want to use one, unless you're doing it for learning purposes, it's best to just use the built-in one rather than trying to roll your own. But with that said, there are some potential trade-offs that, like I mentioned, that you could deal with, but also if you are going to use one of these standard template library containers, I would at least recommend that you try to implement it yourself just to gain an understanding of how it works before you go off and start using them. But yeah, so now I want to move into smart pointers, since that's, I guess, potentially where I have a hotter take, I guess, if you will. So if you go onto any kind of forum or Stack Overflow or anywhere where people are discussing C++, if some poor soul makes the mistake of showing their code with raw pointers, basically the C++ community is going to rip them a new one for not using smart pointers, because I guess the words of wisdom, if you will, and I think it's technically even in some style guides out there, like I think the Google style guide for C++ states it, but basically pretty much everyone that's like a C++ diehard will tell you to use smart pointers, and essentially only use smart pointers if you can help it. Now, I think we should probably touch on what the heck are smart pointers and how do they differ from raw pointers, if you will. So, in essence, the reason they're called smart pointers is because they auto-delete themselves when they go out of scope. And they're really good at ensuring ownership of something, which in the world of C++ is really good once you, since C++ is object-oriented, it actually has this idea of objects and ownership and that kind of a thing. So it is definitely very beneficial. And the reason it's beneficial is because you don't run into the issue where you accidentally try to free something that is used by something else, and then when that something else tries to access that memory, it has been freed and you run into an error because you're trying to access memory that's out of bounds. So smart pointers basically kind of handle that for you. So the other thing I mentioned is they auto-delete themselves when they go out of scope. So I think we should kind of touch on what that means for the non-tech savvy programmer developers out there, just so we're all on the same page. So basically what it means to go out of scope is if you declare a variable within a function, once that function finishes executing, that variable no longer exists. It goes out of scope, if you will. So this is where, kind of touching back to the containers, where the stack comes into place. So when you call a function, that new function and all of the memory associated with it gets pushed onto the stack. And then once that function is done executing, it then gets popped off the stack or removed, so all that memory goes away. So if you declare a variable within that function and don't call something like malloc to allocate memory on the heap, once that function goes out of scope, that memory is removed from the stack and the variable is no longer accessible. So the reason why this matters is because if you declare a pointer and allocate memory to it on the stack, like within a function, if you don't free that pointer, the memory leaks or is unable to be freed until the program exits. And the reason for this is because while, yes, you allocated memory on the heap so it won't go out of scope, the problem is the variable that's pointing to that memory does go out of scope, so you lose access to it, thus leaking the memory because you can't get it back. So that's one benefit to the smart pointers, is because when they go out of scope like that, they will auto-delete themselves and free all the memory associated with them. So it's definitely very beneficial at, it's not leak-proof, but it does a very good job at preventing simple memory leaks like that from happening. Now, in addition to talking about memory leaks, in general, for quick programs, it's honestly not that big of a deal. Like if your program is like a one-time thing that runs once and it's done, it's not necessarily a huge deal. I mean, it's definitely best practice to free your memory. But it's not like the end of the world if you accidentally forget to call free and your program is only running for like 2 seconds. But it's a completely different story if you're building a server, for instance, because if you're creating a server that's essentially has to be on all the time, if you have memory leaks in there, yeah, a couple bytes here, couple bytes there might not sound like much, but when that thing's running 24/7 and it's leaking a few bytes here and there every minute, every hour, that's going to build up over the course of the runtime of the program, and you'll eventually get to the point where your system is completely out of memory because you've leaked it all. So it's definitely best practice to ensure your program is free of leaks, which smart pointers can definitely help you with. So there's 3 main kinds, I guess, if you will, of smart pointers. There's the unique pointer, the shared pointer, and the weak pointer. But in my experience, it's the main ones that people tend to focus on is the unique pointer and the shared pointer. The weak pointer, at least in my experience, isn't used as much. But the unique pointer is essentially only one reference to the pointer. The shared, like it kind of implies there's multiple references to it. And then the weak pointer is essentially a reference to an object held by a shared pointer. But the key thing with the shared pointer, though, is the reason why it's able to ensure that memory is deleted at the right time is because it has an internal counter to essentially count how many references to that pointer there are, and then once that value reaches 0, then it frees and deletes itself. Of course, if you're using a unique pointer where there's only one reference, you don't have that issue, but that's one thing with the shared pointer is it essentially keeps an internal counter. But as you might be able to guess here, that's not without some overhead. Because having to keep that internal counter does accrue some overhead. But one thing I also mentioned with these smart pointers is they're sort of leak proof. I mean, they're not actually, but if you're dealing with like primitives or your things like your integers, your booleans, your floats, that kind of a thing, it kind of is in a way, because if you're just, say, using only unique and shared pointers, I mean, if you're using like primitives exclusively with them, it's basically, I'm not going to say it's impossible, but it's almost impossible to leak memory, and you almost have your own mini version of garbage collection, if you will. Because the nice thing about the primitives is you don't have to declare your own destructors. So if that term is foreign to you, basically in C++, for instance, when you're creating an object, you're creating a class, you don't have to, but if the class allocates memory, the point of the destructor is to ensure all that memory gets freed. So if you don't implement it properly, whenever your class goes out of scope, it's going to leak memory. So that's kind of the point of the destructor, is to free that memory. And also you have to ensure you have a copy constructor, which will be able to, like if you pass your object by value or something, that memory gets copied, and you also in there have to ensure the memory gets freed. So if you're creating classes and dealing with classes with smart pointers, they're not leak proof, because you could mess up the freeing of the memory for your class and cause leaks that way. Because even if the pointer gets deleted, if the class itself doesn't free its memory when it goes out of scope, you're still going to leak memory anyway. But yeah, but going back to the primitives, if you basically made a for loop where inside the loop you created a unique pointer and say you called new on it to allocate memory for, say, an integer, and you never have to call free, none of that, and you still won't leak any memory. Where if you were using raw pointers like with C, and you essentially said, int pointer is equal to malloc, and then you allocate the size of one integer, and don't call free on it, you're gonna leak memory every single time. So that is one nice thing about the shared pointers, is that they will essentially auto delete themselves. So now comes the question: if these pointers auto delete themselves, what is not to like about them? And I'm going to be honest with you, they do seriously make your life a heck of a lot easier. You don't have to worry about ensuring that, did my pointer go out of scope, having to track down really ambiguous memory leaks because things not being deleted properly. So it is very nice for that. But specifically when it comes to shared pointers, I touched on this a little bit ago, there is an overhead to them, and it does have an impact to performance. So I'm going to link a paper in the show notes below that you can peruse at your leisure if you really want to kind of get more into the weeds. But in essence, I did try some of the experiments that they lay out in the paper for some of the performance differences. And even with optimizations turned on, there is still a performance hit using shared pointers compared to raw pointers when it comes to certain operations when dealing with pointers. Which in contrast, though, with the unique pointer, where it doesn't have that internal counter, if you turn optimization on, it's basically the same as a raw pointer, which is kind of the theme here when we were touched on the standard template library containers. Once you turn optimization on, pretty much any discrepancy that you had without optimization is basically gone. But that's not to say that these smart pointers don't have overhead, because all of the smart pointers do accrue overhead upon creation and deletion, and they will be slower in that sense compared to your raw pointers. But again, once you turn optimization on, it's basically a non-issue, unless I guess you're talking with shared pointers, then there's a little bit of extra overhead. But my, I guess, gripe with them, aside from performance, I guess, because part of the goal, for instance, of my video game project I'm working on is to try to make it as efficient and optimized as possible. So potentially having shared pointers, I guess, for instance, could potentially cause some performance hits. Would it make my life easier? Oh, I'm sure it would. Which actually, trying to think. When I first started, I know I did use some smart pointers. I forget if they were shared or they were unique. I forget which ones I used. But then I transitioned to what the C++ developers would tell you not to do, which is use raw pointers. But anyway, the gripe I have here is, in my opinion, it almost promotes sloppy code. And what I mean by this is, in C and C++, if you're not using smart pointers, you're basically in charge of managing all your memory, which is extremely powerful. But if you don't know what you're doing, you can really shoot yourself in the foot. But having to be conscious of the life cycle of your pointers, understanding what scope they're in when they go out of scope, what's pointing to what, it really forces you to really understand the ins and outs of your program and the architecture of the life cycle of code in general, because you can't afford to just haphazardly create these pointers and not have to worry about them like you can kind of sort of get away with smart pointers. Like, for instance, we talked about, writing a function where you allocate memory. If you don't free that memory within that function or return it and free it later, you're going to cause a memory leak. Whereas if you're using smart pointers, that's basically not an issue. Of course, assuming you take the precautions if you're using a class that you created yourself to ensure that the destructor and all that stuff's good for deallocating all the memory. But in essence, if you're using smart pointers, you can sort of throw caution to the wind and don't necessarily have to care as much about where and when you're allocating and deallocating your memory, because that's basically all kind of handled for you. Which if like some of the older like C and C++ developers that I've talked to before, one of the big reasons why they really dislike languages like Java is because they don't have access and the ability to manipulate the memory themselves, because Java essentially handles all that for you behind the scenes. And in a way, smart pointers, they don't exactly do that, but they kind of do a similar role. Like, for instance, when you create a smart pointer, like, you still have to like allocate memory to it and whatnot. But as far as like the deallocation process, that's kind of sort of handled for you. So in essence, like the thing with smart pointers is you kind of almost have your own version of garbage collection in a way. I mean, like I mentioned, not actually, but sort of. Now, maybe it's just me being so ingrained in C over the last few months, since pretty much aside from the video game that I've been developing, most of the, side projects I've done have pretty much been in C. So maybe it's just that with all the C development I've been doing and basically not having access to things like smart pointers and having to use raw pointers and all that stuff, maybe I'm just like that old man that's mad at the kids these days that don't know how good they have it, since when the old man, me, was their age, I had to walk 10 miles to school, uphill both ways, of course, through 10 feet of snow every single day. You know the story. Maybe that's what I've turned into, having dealt with C with so much. But at the end of the day, though, the standard template library containers and smart pointers are honestly fantastic. And honestly, I'd recommend using them. But for me, one thing that I find incredibly satisfying is when you do something yourself. Like, I think there's a saying out there somewhere where it's like, if you're given something, it doesn't have as much meaning to you as if you had to work for it to get it yourself. So like, if you are managing all the memory yourself and having to do all that manually, at least to me, there's kind of more of a sense of accomplishment tied to it than if I'm just kind of haphazardly allocating things and they all just kind of get deallocated for me, or all of my data structures get automatically resized for me and I don't have to worry about it like actually implementing them and that kind of a thing. I can just call the constructor and it'll make it for me and I can just use the functions. There's something, at least to me, about doing it yourself that I just find value in. Now, that's not to say that I rolled my own standard template library, because I'm not that crazy. I am using the standard template library. But for me, at least, especially when it comes to memory management, having that power to manage memory and all the memory the program uses for the entirety of its runtime, from allocating arrays, deallocating memory, resizing things, like having all of that power and being able to manage it effectively and not leak anything and still have it be very performant and optimized is honestly just so satisfying to me. Now, maybe I'm just crazy because I get, a kick out of doing all that. But, it's something I find a sense of accomplishment in. But all this to say, there's a reason that these things exist, right? There's a reason why you chose to develop in C++ rather than C, because if you didn't want to use any of the features granted to you by C++, you should just use C, because it's better than C++ if you're not going to use any of the features that C++ provides. If you're just going to write C code, there's no sense in compiling it with the C++ compiler. Just use GCC. So if you're if you're using C++, probably the reason you're using it is for things like classes, templates, smart pointers, containers, the improved standard template library, actually having strings. There's a lot of reasons why you'd want to use C++ over C. And if you're going to use C++, I mean, honestly, you might as well use the included smart pointers and containers provided to you, because once you get to the point of releasing your code, you're going to have optimizations turned on, at least you should, when it comes time for release. And once you turn on those optimizations, you're really not going to see any kind of difference in performance compared to if you just kind of rolled your own implementations and wrote all the code yourself. But I guess the last thing I'll touch on, because I know we're kind of running a little long here, is the other nice thing that I have kind of neglected to mention when it comes to the standard template library containers and the smart pointers is it makes your code a lot more concise. So if you've ever written, a lot of C code, there's a lot of lines you have to do compared to, using like a standard template library container where you just call a single function and you essentially condense like potentially 5 lines worth of C code into a single function call. So there is benefit to using these things, because it can definitely make your code a lot more readable and concise. You don't have a bunch of those checks to make sure the memory you received is valid and ensuring that your size isn't bigger than the space you have allocated. And there's definitely a lot of quality of life improvements for sure using the standard template library containers and the smart pointers. So in essence, I think it's safe to say that unless you have a valid reason not to use them, you might as well use them, and it'll make your life easier, and it honestly really won't impact your code performance that much. Because let's also be real here. If you're writing C code or C++ code, you would honestly have to royally mess it up in order for it to run slower than something like Python or Java. So even if you do, maybe sacrifice a tenth of a second because you're using a shared pointer rather than a raw pointer, or because you used a vector rather than a fixed size array, you're still going to beat the pants off a similar program written in Java or Python or some other higher level language that doesn't compile down to machine code. So in essence, we're really like, scrapping over pennies here, and it really honestly doesn't make a whole lot of difference. So yeah, to summarize, for me personally, I like the sense of accomplishment of doing things manually, even if it potentially might make my life harder. I just kind of feel accomplished by doing that. But in essence, use the standard template library containers and the smart pointers because it'll make your life easier. And in all honesty, you're not really going to sacrifice that much performance. But yeah, kind of potentially a hot take, not wanting to use those things, which pretty much everyone tells you to use. And then, of course, I kind of go here at the end and say you should use them anyway, kind of coming to the same conclusion. But hopefully this was enlightening to you to kind of understand how the smart pointers work, how the containers work, kind of give you a sense of some of the potential trade-offs that you could kind of weigh, and just kind of, how these things work and kind of some of the behind-the-scenes stuff of this. So hopefully that was beneficial to you. And before we go today, let's finish up with our trivia question, which is, which of the following is not true about the original iPhone? You couldn't rearrange apps on the home screen. The camera was capable of capturing video at 720p at 30 frames per second. There was no App Store originally. Or the CPU was developed by Samsung. If you said the second option, option B, the camera was capable of capturing video at 720p at 30 frames per second, you are correct, because the original iPhone was not able to record video. So it wasn't even able to capture at 720p, let alone 480 or any kind of resolution, because it was not able to capture any kind of video. So that was your trivia question for the week. I'm sure some of the hardcore iPhone fans, probably that was a joke to them on how easy it was, but I assume some people might have got tripped up, but hopefully you, the listener, hopefully you got it right. And if you enjoyed this episode, if you enjoyed our deep dive into the C++ standard template library containers and smart pointers, definitely share this around, give it a like and review. And if you have any questions about this episode, since I know we kind of tackled a lot, or if you have topics or questions or ideas for future episodes, definitely shoot me an email at contact@darkassassinsinc.com. The link for that is down in the show notes. And that is going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.